Why do we have hands? To pick up stick, to pet the dog, to shake fist at clouds, and perhaps most importantly of all, to drink beer. I think everyone should be able to enjoy a nice cold brew, even robots, which is why our project is about building hands for a robot, so they can drink beer. Oh, and also humans, I guess. Our project took inspiration from a robotic bartender that one of us made as a capstone project for another school. The robot they were given was weaker than a toddler and entirely unable to pick up full-size pop cans, so they had to resort to mini cans and putting double-sided tape on the hands for grip.
Take the drink.
But what if there was a better way?
From the moment I understood the weakness of my flesh.
There are a multitude of different end effectors that we can go with. These can be broadly grouped into two different groups, non-mechanical and mechanical. Non-mechanical consists of methods that don't involve using actual claws to close onto the object. These are things such as vacuum grippers, which work by creating a seal along the object. Another one is electromagnetic grippers. These work by using electromagnets to hold onto metallic surfaces. Main setback of these is that they need a flat surface to be able to work efficiently. From there, we then go to mechanical grippers. When you think about claws, these are the ones you think about. The design we decided to go with was just the standard 2 to 5 claw gripper that operates essentially like a robotic hand grasping onto the object. Now, from there, we also have material considerations. We could make this thing out of titanium if we wanted it to be the absolute strongest we can get. However, that's a bit more of a niche use, mainly in aerospace or prosthetics. This is meant to be a general use. Instead, if we were wanting to stick with metal, we can instead go with aluminum. Aluminum is considerably cheaper than titanium, and for the most part it has the same durability as titanium, a little weaker, but holds up pretty well. However, aluminum has a high machining cost as well. From there, we can then go with 3D printing. Good old plastic, everyone's favorite. Plastic, well, it's very easy to break. It's also very cheap, making it really nice if we're prototyping these designs or if we want these designs to go out to everyone. So we decided, let's go with 3D printed plastic, make this nice and easy. And thankfully, we don't need to worry a whole lot about regulations. Only regulations we need to worry about from an engineering standpoint is it can't break human bone. That is the only engineering regulation we need to look out for when it comes to grippers. Generally, the lower limit for the force is about 60 to 65 newtons. This shouldn't break any human bone, even the most fragile.
Due to the limitations inherent in being students, we decided on 3D printing several designs to test and determine which one could be considered the best for our purposes. This is due to economic and accessibility factors. The design process started with deciding what our goals would ultimately be. For our general solution, we wanted something that could effectively replace a human hand for everyday purposes. This meant that, aside from considering how well it could pick up a pop can, the claw design should also be able to pick up a variety of objects without major issues. The robo-bartender solution only has to contend with objects the size and shape of a pop can, but due to the weakness inherent in our inspiration, we also wanted to consider the weight of our final choice. Thus, whatever we ended up designing needed to follow a certain set of criteria. Weight, grip strength, stability, cost, and durability were our top considerations. Though we could compare our manufacturing method to other methods or materials, we would still be able to compare them against each other. Our designs are going to be restricted by two major components. Of course, our claws should be able to pick up a pop can, so that sets our general dimensions pretty cleanly. On the robot side of things, the robot we took our inspiration from had a sliding mount with a gap at most 1.5 inches wide, which limits our designs even further. While some other robot or a different kind of mount would have different considerations, these are the ones that we decided to work within. In the end, we came up with 5 different shapes of claws to test. In addition, we wanted to see if any style of grip would make a difference in the performance of the claws. So, after the claws were finished printing and our testing apparatus was assembled, we got to work.
We began by testing different surface frictions to see how much that would affect the grip of our claws. We tested a rough surface by sanding one of our claws, adding double-sided tape or hot glue to the surface, and by stretching a balloon over a claw. After comparing results to a control, we found out that hot glue came out ahead as the best surface friction we tested. We applied this surface friction to each of our different claw shapes and tested them against a variety of differently shaped objects to see how effective they were in everyday scenarios. When deciding how well each claw performed, we had to consider that a robotic bartender would have different criteria to be considered successful compared to our general solution. By comparing the different claws against each other, we concluded that the best shaped claw for a robotic bartender was either claw B or C, or even a combination of the two in order to account for different bottle shapes. Our general solution winner was claw C.
Each claw had its strengths and weaknesses. The curved claws could pick up objects that the straight one could not, and the simple claws had more strength than the complex claws. Claw C, the triangular claw, ended up winning because of how versatile the shape was when dealing with everyday objects. Plus, it had the strength and durability from its size. Despite claws A and E being designed specifically for picking up beer, our testing concluded that when considering other factors, like weight and cost, claws B and C would work better for our hypothetical robotic bartender. Now, all we have left to do is design the rest of the robot. All of our designs and research are available for free to the public on 3D Content Central. Now, children without hands all across the world can print claws to use on their LEGO prosthetics.